Hi guys, in this video, I'm going to tell you something about the use of vectors and resultant in my everyday living. When I go for a walk, I often find myself applying the concept of vectors and resultants without even realizing it. Take, for example, the act of walking in a straight line. As I push up with my right foot and lift my left foot, I am exerting a force in a specific direction. This force can be represented as a vector with magnitude and direction. Similarly, the force I apply with my left foot can also be represented as a vector. These two vectors can be combined using vector addition to determine the resultant, which represent the overall force I exert as I walk. If the vectors are equal magnitude in an opposite direction, the resultant will be zero, and I will come to stop. However, if the vectors are unequal or in the same direction, the resultant will have both magnitude and direction, indicating the speed and direction of my movement. This is crucial for maintaining balance and stability while walking. Additionally, when I encounter an obstacle or need to change direction, I must adjust the angle and magnitudes of the individual's vector to achieve the desired resultant. For instance, when I turn left, I exert a greater force with my right foot and a lesser force with my left foot, causing a resultant vector that point in a new direction. So, for example, let's say I started at the intersection and walked 50 meters due north along one street. This distance and direction represents the vectors on my first segment. Later, I turned to my right and continued walking for 30 meters due east along the second street. This distance and direction represents the vector of my second segment. To find the resultant, I needed to combine these two vectors through vector addition. By considering their magnitudes and direction, I calculated the resultant vector, which represents the overall displacement and direction of my walk. Using Pythagorean theorem, I found that the resultant vector had a magnitude of approximately 58.31 meters east of north. In simple terms, after completing both segments of the walk, I ended up covering a 58.31 meters with my path deviating slightly to the east from my initial direction. So in this video, I can say that when I walk after school, I realize that I am applying vectors and resultant in my everyday living.
This video will help us to identify which is distance and which is displacement. The first video identify how can I go to that particular house with the actual path, and the other one is that identify that I can use the shortest way or shortest path to go to that particular house. So which is distance and which is displacement? The first video is distance and the second video is displacement. Distance means this is the actual path traveled by a body. So we can see in the first video that I use the actual path to go to that particular house. In the second video, we use the shortest time or the shortest way to go to that particular house. So this is displacement because it's the shortest path between the two locations. And the other difference of the distance and the displacement is the distance is the scalar quantity while the displacement is the vector quantity. And the similarities between the distance and the displacement is they are both need, or they are both require a reference point to be measured from. And that's all. Thank you.
So, in this video, we will talk about speed and velocity and their similarities and differences. In this example, we have point A and point B. Now we introduce an object that can be given motion. Now we give it force. Now we have speed or velocity. So what are the differences? So first, here's again point A. Then we have point B. And then we have a direction in a singular motion. We can call that distance between A and B. Now we introduce an object that can be moved or can have motion. Now that motion would be called, or how fast you can go, is speed. Next up is the formula of distance over time, which would equal to speed. An example, a toy car hit the wall in 10 seconds. If the car's point of origin and the wall has a distance of 25 meters, what is the speed of the toy car? So, of course, the distance we have is 25 meters, and the time that we have is 10 seconds. So, we would have 25 meters divided by 10 seconds, and we will get 2.5 meter per second. That is now the speed. Next up is we have velocity. So, velocity is like speed, but here we have point A and the direction of east. Just like north, east, west, and south. Instead of a point, we go for another direction or the ones in the compass. Now, that is what we call displacement. Then we add the motion that can be given, then it would become velocity because it is relative to its direction. Here we can see that displacement over time equals velocity. Example, a toy boat hit the each side of the pool in 30 seconds. If the boat's point of origin and the side of the pool has distance of 35 meters, what is the velocity of the boat? So, what we have to do here is find again the displacement and then the time. Displacement is 35 meters east and then 30 seconds in time. What we will have to do now is 35 meters over 30 seconds will equal to 1.17 meter per second east. Again, having east for its direction for it to be a velocity. But velocity does not always go linear and it has to be calculated in a straight line. So just like this, 45 meters to the west, 38 meters to the north, and then we would have to find the straight distance or displacement that it has given. With 180 seconds, that is what we have to find. We would have to use the Pythagorean theorem in order to get the missing side or the actual displacement of the said velocity. Here's a real life example. A car going in a single direction.
Moving on, we are now going to discuss what acceleration and deceleration is and how it can be applied in our daily life. So acceleration is a rate of change in velocity while deceleration is a negative acceleration. And in terms of finding the acceleration and deceleration, I prepared one situation where we do in our daily activities, and for it to be connected to our topic, we will also be using formulas that was depend on the situation. So the different formulas that we might be using later are displacement is equals to final velocity minus initial velocity, followed by average velocity is equals to initial velocity plus final velocity over 2. The third one is final velocity is equals to initial velocity plus acceleration times time. The fourth one is displacement is equals to initial velocity times time plus 1/2 times acceleration times squared. And the last one is final velocity squared is equals to initial velocity squared plus 2 times 80. For instance, is like what I said earlier, I prepared one situation where it proves that acceleration and deceleration is applied in our daily activities. So, a car is running at 40 km per hour when the driver starts to step at the brake. If the car decelerates at the rate of 5 meter per second squared, how long does it take for the car to stop? And by analyzing the situation, what do you think are the different given that we will be using? So we have here initial velocity which is equal to 40 km per hour. That will be 11.11 meter per second. Acceleration is equals to negative 5 meter per second squared. And final velocity is equals to 0. The formula that we will be using is formula number 3 because it was looking for the time or how long does it take for the car to stop. But before we substitute the given, let's analyze first how come the given in initial velocity, which is 40 km per hour, be 11.11 meter per second squared, and the changes in signs in acceleration, which is positive to a negative sign. Since in answering a problem in physics or in any situation that needs units, we also need to be consistent in our units. And as I said earlier, that if the given is deceleration, it will always in a negative sign and the unit is also meter per second squared. So as we can see on the given itself, the units in our initial velocity is kilometer per hour. So what we need to do is to convert it into meter per second. 40 kilometer is equals to 40,000 meter. And 40 R is equals to 3,600 seconds. After converting, we are now going to divide them to each other. 40,000 meter divided by 3,600 second is equals to 11.11 meter per second. In addition with that, I know many of you were asking where did the zero in final velocity comes from. Simply it comes from the word stop or brakes. After doing the whole process to get the right unit and finding the given, it was now ready for substitution. And using the third formula, which is final velocity is equals to initial velocity plus acceleration times time, 0 is equals to 11.11 meter per second plus negative 5 meter per second squared times time. So our answer now is 2.2 seconds. So the car will take 2.2 meter per second for it to stop.
Next topic that we're going to be talking about is free fall. Here we can see a feather, and then here we can see an anvil. When they are dropped, the anvil drops first, and the feather sort of just floats around before it lands. But that is not because of gravity. It is because of air resistance. Since the thing is lighter, or the feather is lighter, that means that the anvil is much more heavier and resistant to the wind. But if you were to put the two items together in a room, or in a vacuum room, they would both fall down in the same time. Because again, there is no air, and there is no air resistance to go to. Therefore, we have what we call free fall. And in free fall, this is what we can see. There are many different formulas that can be used in order to determine final velocity, distance, uh, final velocity, or squared final velocity. In all of these three, there is one common thing. There is g, or acceleration due to gravity, which is 9.8 meter per second squared. Final velocity can be got with initial velocity plus g times time. Then distance would be initial velocity times time plus 1/2 times g times time squared. Then final velocity squared would be got with initial velocity squared plus 2g times distance. And that includes everything that should be known in the formulas. Next up is we can see the many or one of the examples of free fall. Just like that of velocity, free fall has many different formulas that one can use in order to get the other elements. Just like how you can transpose or manipulate the formulas in order to get other things that are needed in the formula. For example, we can get in the distance one, we can probably get the time in order by just manipulating the different elements of this same equation. Same goes for the final velocity with vi and the other things. But one thing that we cannot manipulate in free fall is g, or acceleration due to gravity. It is an important part of this sort of free fall or this sort of engagement. So we must always remember the formulas, and we must always remember g, or what we can say is the acceleration due to gravity, because it holds so much importance for free fall and the many formulas it uses or elements it uses in order to get what it needs to be got.
Good day to all of you. I'm Christopher Braille Dilascano, and in this video, I'm going to talk about friction with regards to two solid bodies. And also, I'm going to discuss the types of frictions that there is. But first, what is friction? The rubbing of one body against another. From that statement, we can already tell that friction happens when two solid objects are connected with each other. Friction is a kind of force, opposes motion, and is acting on two objects that are connected with each other. So basically, any two solid objects that are connected with each other already has friction. What I'm doing right now is already a friction because the two solid bodies are connected with each other. The eraser is at rest with the whiteboard, and that is still called a friction. It is a type of friction that we call the static friction. Static friction is defined as the frictional force that acts between the surfaces when they are at rest with respect to each other. So basically, this eraser resting on a whiteboard is a example of static friction. The next type of friction that we have is the sliding friction. Sliding friction is defined as the resistance that is created between any two objects when they are sliding against each other. So, a great example would be this eraser and whiteboard. When we slide the eraser to the whiteboard, it creates resistance and it is already called a friction because they are connected with each other, and since they are sliding, it is called a sliding friction. Another fact about sliding friction is less when the surface is smooth, just like this whiteboard. And the resistance gets greater when the surface is rough. Take this as an example. This whiteboard is smooth, so the resistance is not so much. While in this wood, the resistance is greater because the wood is rougher than the whiteboard. The next and the last type of friction that we have is the rolling friction. Rolling friction is defined as the force which resists the motion of a ball or wheel and is the weakest type of friction. So basically, when two solid objects are connected with each other and has the ability to roll, it is considered as a rolling friction. A great example would be ball rolling on the floor, bicycles, and gaming chairs, or anything that has wheels on it. It is also mentioned that rolling friction is the weakest type of friction. Why? Because unlike static or sliding friction, rolling friction has the least resistance. Take this as an example. This is a sliding friction, and this is a rolling friction. Here is an example of rolling friction when applied in real life. Friction that consists of wheels is very practical and is mostly used in today's world, just like vehicles that we use to make our life easier.